Okay, welcome back, students. We're going to take a look at the renal corpuscle, or the Bowman's capsule, a little bit more. So the renal corpuscle consists of two parts. It's that glomerulus, which is the mass of capillaries, and it's fed by the afferent arterial, and it's going to drain into the efferent arterial. The glomerular capsule, or Bowman's capsule, has a layer around it of podocytes, which also wrap around the capillaries. And these podocytes are going to create these little filtration slits that are going to allow certain things to pass through there. So here's the afferent arterial. Here's the efferent arterial. You can see that this one is more open and dilated than this one. So blood comes in at a faster rate than it can exit. Here is the capsule itself, right? The Bowman's capsule right here. And this is the beginning of the proximal convoluted tubule. You can see the cuboidal cells here. Right here in the center, this is the glomerulus. And what surrounds the glomerulus are these little podocytes. The podocytes wrap around and create these little regions of filtration, and there's a few different layers that allow filtrate and allow certain things to come out to become filtrate to pass into the peritubular, to pass into the proximal convoluted tubule. So this shows the filtration slit. So this is a podocyte here. And then you can see we've got like one, two, you got three different layers here. You have the fenestration, or the pores of the glomerulus, which prevents the filtration of blood cells, but allows all the components of the blood plasma to pass through. And then the second layer prevents the filtration of the larger proteins. And then the slit membrane between the pedicels, it prevents filtration of medium or medium-sized proteins. Okay, so you have these different layers that will only, they're permeable, but won't allow large proteins to pass through there. If there's a large amount of proteins that pass through and it's picked up on a urine test, then it's safe to assume that there is some severe damage to the nephron, or severe damage to what we see in here as part of the nephron, because we don't want to see that pass through. So here's a neat look at that capsule again. So we have an afferent arterial down here on the bottom. We have the efferent arterial here. You can tell by the way the arrows are coming in. Here is a podocyte that creates these different filtration layers and filtration slits going around the glomerular capillaries. Here's the capsular space. So the filtrate is pulled out here, right, into this capsular space, and eventually we'll move into the proximal convoluted tubule. Now, after the proximal convoluted tubule, right here in purple on the top, sorry, this is the Bowman's capsule still, but right after that purple section, you're going to have the proximal convoluted tubule, and then we follow it around. We've got that descending limb, and remember, the descending limb was thinner because it was more squamous cells, so you got that thinner part here. And then the ascending limb was thicker, and here's the actual loop. Then you've got the distal convoluted tubule coming around. So right here is the distal convoluted tubule that we can see right here, right between the afferent and efferent arterioles. So if we look down on the bottom, here's the distal convoluted tubule, and it's right between the afferent and efferent arteries. And there's important cells that line that distal convoluted tubule that are referred to as macula densa cells. These are macula densa cells. And right here, near the afferent and efferent arterioles, we have what's called JG cells, or juxtaglomerular cells. Okay. When we combine these together, the macula densa cells and the JG cells, they just call it the Juxtaglomerular Complex. And it's an important region. The Juxtaglomerula Complex is the region where the distal convoluted tubule comes into contact with the afferent arterial. And the macula densa cells and the juxtaglomerular cells are important because they're involved in secreting erythropoietin, EPO, and renin. And EPO is going to increase the red blood cell production, and renin is involved in knocking off angiotensinogen, or at least activating angiotensinogen into angiotensin 1. So these regions are very, very important in regulating this juxtaglomerular complex here is really important because of the macula densa cells and the JG cells in regulating blood pressure and red blood cell production. So the macula densa cells, these are packed modified columnar cells, and they're located in the wall of the initial part of the distal convoluted tubule where it passes the afferent and the efferent arterial near the glomerular capsule. And it's adjacent to the juxtaglomerular cells. And they're going to act as like chemoreceptors. They're going to sense changes in salt concentration or sodium chloride concentration in the filtrate. And it's going to send signals to the juxtaglomerular cells to secrete renin. So the JG cells, these are modified smooth muscle fibers in the walls of the afferent arterial, and these act as like mechanoreceptors. They're going to sense blood pressure in the afferent arterial. They're going to sense blood pressure in the afferent arterial. And if blood pressure decreases, renin is released, and renin leads to an increase in blood volume and blood pressure. The JG cells contract when stimulated either by stretch or by the sympathetic nervous system. Okay. So these shouldn't say baroreceptors. These should say like baroreceptors, pressure receptors. You should say baroreceptors. Chemoreceptors in the kidney. Chemoreceptors are going to monitor oxygen levels. So if oxygen levels fall, the JG cells are going to release more erythropoietin. The erythropoietin goes to the bone marrow, and that will increase red blood cell production through what's called erythropoiesis. Erythropoietin increases erythropoiesis, which just means increase in red blood cell production. So here is where renin comes into play, right? You have angiotensinogen that's made by the liver. Okay, so on the bottom left here, we see the liver, and we see it makes angiotensinogen, but we see that our good friend the kidney produces renin. And renin converts angiotensinogen by knocking off OGin and giving us angiotensin 1. So angiotensinogen becomes angiotensin 1 because of renin. Now angiotensin 1 becomes angiotensin 2 because of ACE, angiotensin converting enzyme, ACE, angiotensin converting enzyme. So here's the angiotensin 1 being converted into angiotensin 2 because of angiotensin converting enzyme, which is ACE, ACE. Angiotensin 2 is going to vasoconstrict blood vessels. When you vasoconstrict, you're going to increase blood pressure. It also, angiotensin 2 stimulates the release of aldosterone. Aldosterone is responsible for allowing us to reabsorb sodium. If you reabsorb sodium and you reabsorb water, you increase blood volume, blood pressure increases. What a beautiful cascade of events that happens here. Isn't that something?